Okay, so let's look at our first problem here. We have x squared plus 3x minus 40. First thing we do is, do we have any factors in common that we can factor out of all three of these terms? The answer to that is no. We know that this is not a perfect square trinomial, although x squared is a perfect square, negative 40 is not, nor is it a difference of perfect squares for the same reason. So that means we're going to be using sums and products. And because our coefficient here is still just 1, we'll look at what happens when that's not 1 later, we know that we're going to have an x times an x. Now we need two numbers, we'll make this little diagram here, that multiply to negative 40, but they add to positive 3. Well, those two numbers will turn out to be positive 8 and negative 5, which means our factorization, that x should be over there. And let me get rid of this. And so we end up with a factorization of x plus 8 times x minus 5. Okay, for our next one, going through the same process, nothing in common to factor out, not a perfect square trinomial, not a difference of perfect squares. So again, we're going to have sums and products. This time, we have the two numbers needing to multiply to positive 2 and adding to positive 3, which is going to give us the two numbers 2 and 1. So we're going to end up with p plus 2 and p plus 1. One thing to keep in mind, sometimes you forget, or it's easy to forget, that these numbers on the end, one of the factorizations is the number times 1, but sometimes that is the factorization that we need. Okay, let's take a look at this next problem here. All right, so now we have something a little more complicated looking, and in fact, in this case, we have two terms, and we have a difference, and they're both perfect squares. And again, we can tell because the 9 is perfect square, the exponents for x and y are even, and the exponent for z is also even. So our basic pattern is a squared minus b squared is equal to a minus b times a plus b. And what that means is that we can factor it into, we need to find the square roots of each term. So we have 3xy squared, that whole quantity squared, minus z to the third, that quantity squared. And so that gives us our a and our b, and so we end up with a minus b, or we could do it in reverse order, times a plus b. Okay, so this is considered fully factored because it consists now of just the product of one factor times another factor, and we cannot factor further either of these two binomials inside the parentheses. Okay, let's look at the next one here. Okay, first thing we see is that this time we actually can divide out something. So we do as our first step, 49q squared minus 14qs plus s squared. So we factored it once, and now the question is, can we factor it again? Well, we look at this, no more common factors, but we do have a difference, or rather a perfect square trinomial, because 49q squared is a perfect square, as is s squared. And when we take the square root of that, 7q, and we multiply it by the square root of this, s, and we double it, we get our, in this case, negative 14qs. So the factorization pattern here is a squared plus 2ab plus b squared, and that factors to a plus b squared. So in this case, our two square roots are 7q and s. And so we're going to end up with, in this case, 7q minus s squared, which is our factorization just of what's in parentheses here. And we can't forget this q, okay? Easy mistake to make. So this is our final factorization. Okay, let's take a look at the next one. This is a pattern that I want you guys to be familiar with because you will see it, and it's an easy one to miss. Okay, so let's look at what's going on here. So we have one term here and a second term here. Each term has this factor, and then this has these two factors. So what we're looking for first, as always, is do we have any factors in common? And here we in fact do, but it's not necessarily so easy to recognize. And what we have is p minus 3 and its opposite, 3 minus p. And these are just negatives of each other. And so we can actually convert this to being the same factor, this the same factor as this. So we're going to rewrite this to make it p minus 3 times 2q plus 5. Now, since this is going to be negative, it's going to be minus p minus 3 times 5 minus q. So what this gives us is the ability to factor out this common factor from both of these terms, which gives us p minus 3. And then inside, and I'll use square brackets this time, we have left 2q plus 5, and we have minus 5 minus q. Square bracket. That's the square brackets I'm using just because it's to make it a little less confusing so we don't have too many parentheses. All right, so what's inside the parentheses we can simplify. So we're going to have p minus 3. We're going to have 2q plus 5 and then minus 5 and a minus negative q, which gives us a positive q. So we're going to end up here with 3q. That's 2q plus positive q. And positive 5 minus 5, so that becomes 0, so this is what we end up with. Okay, next one here. Again, a little more complicated, but the thing to recognize is that we do have here an a squared minus b squared pattern. And again, we know that that factors to a plus b times a minus b, except in this case, our a is equal to 2x minus y, and our b is equal to x plus 3y. So our a plus b is going to be equal to, so our a plus b, we ended up with 2x minus y plus x plus 3y. And over here, our a minus b, we had 2x minus y minus x minus 3y. And when we simplified, oh, by the way, be careful here because this negative 3y, because we were subtracting a positive, this becomes a negative, and so that's a very easy place to make a mistake. So when combined, we end up with 2x plus x, negative y plus 3y gives us 3x plus 2y, and over here we end up with x minus 4y. Okay, so now let's take a look at the next one, and we have 4 terms here. And what we said we would do in that situation is look to see whether factoring by grouping can help. So let's take the first two and think about what's the largest common factor for these two. Well, we could say this is equal to 5x squared times what's left here would be 2x plus 3. And the 6x plus 9 we can say is equal to, factoring out the greatest common factor, 3 times 2x plus 3. So our whole polynomial now can be rewritten as this. And so we have 5x squared times 2x plus 3 plus 3 times 2x plus 3. So we now see we actually have, with these two terms, again, two terms separated by a plus sign, we have a common factor, which is 2x plus 3. When we take that out, what's left is, here we have our 5x squared, and here we have just our 3. So that's our factorization for this 4-term polynomial. All right, so let's keep going here. Let's go on to the next page, and let's move this page out of the way. And we're going to do a little work with trying to solve some equations. Now, this first one you see we've set equal to 0, and if you recall the zero product property, what it said was that if we can get some factors multiplied together to equal 0, then we can solve separate equations for each factor and come up with the solutions that make this true. So in this case, let's make this a little bigger here. So we'll say in this is going to be factored by sums and products, and it's going to give us x plus, and we need two numbers that multiply to 8, add to 6. That's going to give us 4 and 2. And we know that these multiply to 0, and so that gives us these equations. We know that either x plus 4 is equal to 0, gives us one solution, so x is equal to negative 4. Our second solution comes from x plus 2 being equal to 0, which gives us x is equal to negative 2. So if I plug in either negative 4 or negative 2 into this, I will get 0 times the other term, which is going to give me 0. So there are two solutions, and we found them both. Okay, looking at the next one here, we can see that we don't have that same setup. We have x squared minus 3x is equal to 28. So what we're going to do is, and we'll be doing this a lot, you'll see it frequently, is we're going to set this equal to 0 by subtracting 28 from both sides, and that's going to give us, on the left, an expression that hopefully we'll be able to factor, and on the right, 0. So again, this is factorable by sums and products because we need two numbers that multiply to negative 28, add to negative 3. Those turn out to be negative 7 and positive 4. So we end up with x minus 7 times x plus 4 is equal to 0. And so we get our two equations to solve. X minus 7 equals 0, x plus 4 is equal to 0. X is equal to negative 7, x is equal to negative 4. Sorry, this should be x is equal to positive 7. So let me get rid of this negative sign here, positive 7. Okay, all right, let's go on to the next one. So now we have a case where we have 4 terms. It is set equal to 0, so we want to see, can we factor this using our grouping? So let's do it like this, and we'll say, can we pull out anything common from this first term? Well, yes, we can pull out an x squared, which leaves us x plus 3 minus, and we can pull a 4 out of here, and that leaves us again an x plus 3, all of which is equal to 0. So when we now have, in this, we have an x plus 3 factor common to both of these, so we're going to take that out, factor it out, and what we're going to be left with is x squared minus 4, again, the whole thing equal to 0. But this can be further factored because it's a difference of perfect squares. So here we end up with x plus 3 times x minus 2 times x plus 2, all of which makes equal to 0. So our solutions are x is equal to negative 3, x is equal to positive 2, x is equal to negative 2. What this means graphically, and we'll see this later, is that the graph of this particular function here crosses the axis 3 times, crosses the x-axis, that is. So y is equal to 0 when x is equal to negative 3, when x is equal to 2, or when x is equal to negative 2. Again, we'll see more of that later. Okay. So now we have one more challenge, which isn't written here, so I'll have to update that. I will address that one separately.